Hi, in this video, we're going to look at some more examples of solving problems involving Newton's second law and forces and acceleration. So, in this example, a 0.24 kilogram dodgeball is lobbed towards Sam, who carefully exerts a force with his hands to bring it to rest from a speed of 12 meters per second. During the process, his hands recoil a distance of 0.38 meters. What is the acceleration of the ball, and what is the force applied to the ball? Neglect air resistance. So I've already drawn the situation here, and I've also already gone on and added the gravity pulling the ball towards the center of the Earth. We're focusing in on the ball here as our system, so we're drawing forces acting on the ball alone, not the person. So what other forces are acting on the ball? I guess we could say that since the ball is moving to the right, according to my picture, then there must be a force being applied to the left. Okay, so we're going to label this the applied force here, and that's the force that Sam applies to the ball. All right, so we have this situation where you have two forces. One is horizontal and one is vertical. And we're going to keep things a little bit simpler for the scope of this class. We're not going to concern ourselves with the fact that the net force is going to be somewhere here in the middle of these two forces, which is technically true. When it asks for the acceleration of the ball, though, we're really only focused on the horizontal acceleration. So when you see problems like this, it's not asking you to really consider the acceleration of the ball downwards, because we know that that's always negative 9.81. Instead, we're just going to be focused on this applied force. And so for the horizontal net force is just simply equal to the applied force. And the vertical net force is simply equal to the weight of the ball. All right, it says what is the acceleration of the ball? So that is our unknown number one. We're looking for the acceleration of the ball. We do know some information about the ball. We know that it has a mass, because of the kilograms here, of 0.24 kilograms. We also know that the ball is brought to rest from a speed of 12 meters per second. So you have to translate this information into physics quantities. If it's brought to rest from a speed of 12 meters per second, that means it was going this fast initially. This is our initial speed. So initial velocity of the ball is 12 meters per second, and that's to the right. So it's positive to the right, as you can see over here. This is the velocity. And then it says it's brought to rest, right? And so that gives us info about the final velocity of the ball, that is 0. Okay. We also are given that during this process, the person who's catching the ball, his hands recoil a distance of 0.38 meters. Recoiling is like when you catch it, it comes back in your hands a little bit. So it takes a little bit of time, like a few, maybe a few milliseconds to actually slow the ball down. You don't just hold your hands out and catch it. You got to bring it in. That's the recoil distance here. It's a distance, and so we're talking about the change in the position of the ball during this short slowdown period. And so that's going to be the delta x. The ball travels 0.38 meters to the right as it slows down. So we have a bunch of information here. We are looking for the acceleration of the ball. Now, you probably recall when you're looking for acceleration, you've got it right here in the Newton's second law triangle. So to find acceleration, you can take the net force and divide by the mass. The problem is we don't know what the net force is. We are not told how much applied force there is, so we don't really know this information here. We do know the mass, but we don't know the net force yet. So we're going to have to find acceleration in a different way, and we're going to have to pull on some previous kinematics equations to do so, because we're given the initial speed and final speed of the ball. So that's going to tell us a little bit about acceleration there. We're not given a time value. We don't know how long it took for the ball to slow down. So instead, we're given a displacement for the ball. So we got to look through, the equations that we know for acceleration with these kinds of variables. And the only one that has all of the pieces that we need is this one here. It's the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times delta x. So this is going to allow us to find the acceleration of the ball because we have all these other pieces. So we're just going to substitute in now. So the final velocity is 0. The initial velocity was 12 meters per second. And then plus 2 times the acceleration, which we don't know, so I'm going to leave that as a, times delta x, which is 0.38 meters. All right, so I'm going to start solving now. 0 equals 144 meters squared per second squared plus, and then I'm just going to go ahead and multiply the 2 and the 0.38. So when I do that, 2 times 0.38, I get 0.76. So I'm going to write 0.76, and that's meters. And that's still multiplied by the acceleration. I just took the 2 and the 0.38 and multiplied them together. I still don't know what the acceleration is. All right, so now I'm going to subtract both sides by 144 meters squared per second squared. And do that to both sides so it remains equal. Okay, and that gives me negative 144 meters squared per second squared, and that's equal to 0.76 meters times the acceleration. Now I need to undo the multiplication to solve for the acceleration, so I'm going to divide both sides by 0.76 meters. All right, so that's going to get rid of this over here, and we're going to be left with just acceleration. Notice meters squared per second squared divided by meters, it gets rid of one of the meters here. So what we're left with, after we put this into a calculator, 144 divided by 0.76. So we get, we're going to round it to negative 190 meters per second squared for our acceleration. Now we can check and make sure that makes sense. Does it make sense that the acceleration is negative? Well, the ball is slowing down and it was moving in the positive direction, positive 12 meters per second. And so the fact that its acceleration is negative does make sense. So we've answered the acceleration question. What is the acceleration of the ball? It is negative 190 meters per second squared. But there's a second question here, and that is, what is the force applied to the ball? So in this case, the applied force is equal to the net force. Right, and so because of that, we can use this equation. We want to solve for the net force, and so we're going to take the mass of the ball and multiply by the acceleration of the ball. I'm going to move myself up here a little bit and do it in the corner in a different color. So the applied force, aka the net force in this case, equals mass times acceleration. All right, and so that's going to equal 0.24 kilograms times negative 190 meters per second squared. So 190 times 0.24, that's going to give me an applied force in the negative direction of 45.6. I will round that to 46 newtons. So that would be my applied force there. So that's all I've got for you in this video. Remember, confusion is the sweat of learning.